All right, let's kick things off and dive straight into this paper called Multi-Agent Verification, Scaling Test Time Compute with Multiple Verifiers. You know, it really tackles this tricky issue in AI we always seem to be wrestling with, squeezing better performance out of large language models, or LLMs for short, but without needing mountains of new training data.
It's always that data hunger, isn't it? But what's smart here is they've shifted gears. Instead of just going bigger with models or data sets, they're saying, hey, let's optimize how the LLM thinks during that crucial evaluation stage. They call it scaling test time compute.
So it's not about brute force, more like finesse, making those LLMs more efficient when it matters most.
Exactly. And their secret weapon, this cool concept called multi-agent verification, or MAV. Picture it. A team of smaller specialist LLMs, each like a subject matter expert, giving the big LLM's output a thorough checkup from different angles.
Like a panel of judges, each with their own scorecard on what makes for a winning AI performance.
Perfect analogy. And the best part is these smaller LLMs, they call them Aspect Verifiers, or AVs. They don't need any extra training to work together. They just vote on whether the output is on point or not based on their own area of expertise.
So instead of relying on one big, complex reward model, which can be a real resource hog, they're spreading out the workload, making things more flexible too.
You got it. And get this, they're showing that this team approach with MAV leads to some pretty impressive improvements, especially when you combine it with best of N sampling.
Oh, right. Best of N. Refresh my memory on that one.
It's where you have the LLM generate a bunch of outputs and then you cherry pick the best one. So these clever researchers, they merged that with MAV and came up with this algorithm called BON-MAV. It's like scaling things up in two ways at once. More output options and more specialist judges.
I'm picturing a cooking competition. Multiple chefs, each with their own dishes, and then a panel of food critics, each with their own tastes, voting on the potato.
Love it. And the results? Well, they put BON-MAV to the test across different fields, math, general knowledge, even coding, and it consistently outdid the traditional methods like self-consistency and using just a single reward model.
So this multi-agent verification system, it's not just boosting accuracy, it's like adding a whole layer of robustness and making those evaluations more reliable.
You nailed it. But here's where things get really interesting. They found that sometimes using a bunch of these weaker AVs, meaning smaller, more specialized LLMs, could actually make even those super powerful, complex LLMs perform even better. It's like a team of specialists outperforming a generalist.
Hold on. That's counterintuitive, isn't it? You'd think you'd need equally powerful models for verification.
It does seem that way, right? But it's like they're saying, hey, different perspectives, even from the underdogs, they bring something valuable to the table.
So this weak to strong generalization, it's a bit of a game changer, right? It could mean that folks who don't have access to those mega models can still get great results by using a team of smaller ones.
Absolutely. And they took it even further. They explored this idea of LLMs actually improving themselves, what they call self-verification. It's as if the LLM gets a mirror and is told, all right, critique your own work, see where you can do better.
And did it work? Could they actually boost their own performance by doing this self-critique?
Remarkably, yes, especially those smaller LLMs. They got a noticeable accuracy bump from just this self-reflection. It's a glimpse into this potential future where LLMs become more self-aware, more self-correcting.
Now, this is all very conceptual. Let's get down to brass tacks. How do these aspect verifiers actually work?
Well, it's all about how you set them up. Think of it like tailoring your verification team. You've got three key choices to make. The base LLM you use for each verifier, the specific aspect of the output they'll focus on, and their verification strategy, how they'll do their judging, if you will.
So you could have one aspect verifier, let's say built on GPT-4, going through a solution step by step, making sure the math is airtight, while another, maybe based on Gemini, is looking for any logical fallacies, those inconsistencies in reasoning.
Exactly. And you could even have multiple AVs, all looking at overall correctness, but each tackling it in a different way. One might try to rephrase the solution, making it simpler, while another is all about finding those tricky edge cases, those potential pitfalls.
So it's about harnessing different strengths, different approaches to get a more solid, reliable signal from those verifiers.
Now, you might be thinking, this all sounds like a recipe for complexity. How do you even combine all those outputs from such different verifiers?
I know, right? It's got to be some super fancy algorithm to weigh those votes, right?
Actually, they kept it surprisingly simple. Each aspect verifier gives a simple yes or no, a thumbs up or thumbs down on the solution. Then they just count the votes, and the output with the most thumbs up wins.
It's like AI democracy, majority rules. But for something so straightforward, those results are pretty darn impressive.
Goes to show, sometimes the most elegant solutions are the simplest, but they do acknowledge that this BON-MAV algorithm, it's really just a starting point. There's a whole universe of possibilities out there to explore.
Okay, but let's not get ahead of ourselves. Just how wide-ranging are those possibilities?
Yeah.
What kind of research directions are they pointing to?
Well, for one, they're hinting at going beyond this basic voting system, coming up with more sophisticated ways to combine those verifier outputs. What if, instead of each AV having an equal vote, you could factor in how confident or how specialized each one is?
I like it. Or what if you grouped verifiers based on their specialties and had a two-stage voting system? First, they duke it out within their groups, then the group winners go head-to-head.
And then there's this wild idea, having the aspect verifiers actually debate each other, just like humans might when trying to reach a consensus on something complex.
Imagine a room full of these AI agents passionately arguing about the validity of a mathematical proof or the logic behind some intricate code.
It paints quite a picture, doesn't it? This opens up this whole new world for designing multi-agent systems, systems that could handle even more complex tasks than we can imagine right now.
All right, we've covered a lot of big picture stuff, but I'm itching to get into the nitty-gritty, those experiments they ran. They put this BON-MAV through its paces, testing it across different areas, right?
They did. They really wanted to see how well this approach held up across different tasks and different levels of LLM complexity.
So where do we begin? Math. Coding. I'm all ears.
Let's tackle math first. They use this data set called Math, which is basically a collection of super tough math problems, the kind that really test your logic and problem-solving skills, like the ones you'd see in a serious math competition. It's a great way to see just how far LLMs and those verification methods can really go.
So it's like the AI Olympics of math, huh?
Yeah.
How did our contender, BON-MAV, handle this mathematical challenge?
It totally aced it. BON-MAV consistently beat both self-consistency and that reward model verification across all the different LLMs they threw at it.
Okay, but paint me a picture. What kind of accuracy improvements are we talking here?
All right, so for those heavy hitter LLMs like Gemini 1.5 Pro, they saw improvements around 2 to 3%, which, okay, might not sound like a ton, but in AI, even small wins on these really complex tasks, they can be a big deal.
It's like those tiny margins in professional sports, right?
Yeah.
Every little bit can make all the difference.
Exactly. But for the smaller LLMs, the gains were even more dramatic. Mistral 7B, that's a relatively smaller model, it got a 10% accuracy boost with BON-MAV. That's huge.
Now that's what I'm talking about. It seems like those smaller models,
Yeah.
they really get a leg up from having that team of verifiers backing them up.
That's what the data is telling us. It's like for those models that maybe don't have the strongest reasoning skills on their own, that extra layer of scrutiny, those different perspectives, it really helps make up for their weaknesses.
Now, they didn't just look at the final scores, right? They also dug into how performance changed as they added more candidate outputs and more verifiers.
Yeah, they wanted to see how much juice they could squeeze out by scaling the compute in both those ways. And, in most cases, adding more verifiers, it really did lead to better results, especially for those smaller LLMs. It backs up that idea we were talking about, having more diverse viewpoints, it leads to better decisions, even for AI.
But was there a point of diminishing returns? Like, did they hit a wall where more verifiers didn't really move the needle much?
It wasn't quite that cut and dry. For those bigger LLMs, yeah, the improvements kind of leveled off after a while. Adding more verifiers past a certain point, it didn't really add much value.
Right, because if you've already got a super smart LLM doing the generating, it's probably catching most of its own mistakes already. So at some point, more verifiers, maybe they're not adding as much.
That's the sweet spot they're looking for, balancing that computational cost with how much performance you gain. You don't always need a massive army of verifiers. Sometimes a well-chosen team is all it takes.
So math was a clear victory for BON-MAV. But what about other areas? Did they test it beyond just math problems?
Oh, absolutely. They threw a whole bunch of tasks at it, general knowledge questions, tough graduate-level reasoning problems, even coding challenges. They wanted to make sure this multi-agent approach could handle the heat.
Let's talk general knowledge. They used that MMLU Pro dataset, right? The one that covers all sorts of topics, history, science, law, you name it.
Yeah, MMLU Pro, it's a great benchmark. It really tests a model's understanding of the real world, how well it can reason about all those different areas. And guess what? BON-MAV, it came out on top, that beating both self-consistency and reward model verification across all the LLMs. And just like with math, the smaller models, they saw the biggest improvements.
So this multi-agent thing, it wasn't just a fluke. It seems to work across different types of knowledge and tasks.
You got it. It's not just about math, it's about improving reasoning and problem solving in general. The fact that it consistently outperforms self-consistency, it tells us that having that external feedback, that scrutiny from specialist verifiers, it's really key for getting high accuracy, especially on those tricky reasoning tasks.
Now, those graduate-level reasoning problems, they use that GPQA Diamond dataset, right? The one that's supposed to be super tough, even for us humans.
Oh yeah, that one's a doozy. It's full of these challenging questions from all sorts of fields: biology, physics, chemistry, the kind of questions that would make even a PhD student scratch their head.
So did BON-MA keep its winning streak going against those brainy questions?
It held its own, but the results were a little more interesting. It still generally did better than self-consistency, but on this dataset, it was pretty much neck and neck with the reward model verification.
That's interesting. So maybe for those super high-level specialized problems, having multiple verifiers doesn't give you as much of an edge as using a single, really well-trained reward model.
That seems to be the case. It's like if you're dealing with a very specific area and you can find that one perfect expert verifier, then the benefits of MAV might not be as noticeable.
Makes sense. All right, we've covered math, general knowledge, and graduate-level reasoning.
Bruh.
What about coding? Did they put BON-MAV through any programming challenges?
Absolutely. They used this benchmark called human Eval. It's a set of Python programming problems that are designed to test how well a model can understand code, write code, and reason about algorithms. It's like a coding exam for AI.
So how did BON-MAV do on its coding exam? Did it pass with flying colors?
On human Eval, it performed about the same as reward model verification, but both of them clearly outshone self-consistency. So what that tells us is that having some kind of external verification, whether it's from a single expert or a team of specialists, it's super important for getting those code generation results up to snuff.
Yeah, coding, it's all about precision and getting those details right. Having that extra set of eyes, that external system to double check for errors and make sure the logic is sound, that's got to be crucial for getting good code. Now, I want to rewind a bit and go back to that weak to strong generalization idea. It's just so wild that you can actually improve a really powerful LLM by using a bunch of weaker ones as verifiers.
I know, right? It really changes the game when it comes to making LLM optimization more accessible and scalable. Training and using those top-tier LLMs, it takes a ton of computing power and resources. If you can get similar results with a group of smaller, more readily available models, well, that's a huge win for everyone.
It's like democratizing AI development, right? More people can get involved, even if they don't have access to those massive models.
Exactly. And their experiments show that it's not just some theory, it actually works in practice. They took their strongest generator models, the big guns like Gemini 1.5 Pro and GPT-4o, and then they used Aspect Verifiers that were built from weaker models like Gemini 1.5 Flash and GPT-4o Mini.
And they still saw those big accuracy boosts, even with those weaker verifiers.
That's right. What it's suggesting is that the combined intelligence of a bunch of specialists, even if they're not individually as strong, it can sometimes beat out the knowledge of a single expert. It's like the old saying, 2 heads are better than 1, but applied to AI.
Now, they took that idea even further with self-improvement, where an LLM uses versions of itself as those specialist verifiers to critique its own work. It's like giving the LLM the ability to do its own peer review.
Exactly. They basically gave the LLMs a chance to look in the mirror and see how they could improve.
And did it work? Were those LLMs actually able to improve their own work just by doing this self-reflection?
Surprisingly, yeah. They found that this self-verification thing, it actually led to some pretty decent accuracy improvements, especially for those smaller LLMs. It's like they're hinting at this future where LLMs could become more self-aware, more able to catch and fix their own mistakes. That's a pretty exciting thought.
It really is. So we've covered a lot of the high-level stuff, but to really understand how those aspect verifiers tick, we need to get down to the nitty-gritty of those prompts they used, right?
Absolutely. Those prompts, they're like the instructions that tell those verifiers what to focus on and how to do their job. They're super important for getting the right kind of verification behavior out of those LLMs.
Walk me through it. What do these prompts actually look like?
They've got 2 parts. The first part is what they call a domain-specific system prompt. It's like setting the stage for the verifier.
So if we're talking about the math data set, that prompt might be something like, you're a math whiz, and your job is to figure out if this solution is correct.
Exactly. And for that MMLU Pro dataset, it might be something like, you're a general knowledge expert, here to check if this answer is valid. The system prompt basically tells the verifier what kind of task it's dealing with.
Makes sense. Now, what about the second part of the prompt?
That's the domain-independent verification prompt. It's more specific, telling the verifier exactly what to look for and how to do it.
So for example, if you want the verifier to check if a math solution is correct and you want it to go through each step carefully, what would that prompt look like?
Something like, look at each step in the solution and make sure there are no math mistakes. If you find an error, stop right there and say, incorrect. But if you get to the end and everything looks good, say, correct.
Nice and clear, no room for misinterpretation there. It's fascinating to see how much thought goes into designing these prompts. It's like a whole new level of prompt engineering, all geared towards getting those LLMs to do exactly what you want them to do during verification.
You nailed it. It's like you're programming those verifiers, but with language. And even small tweaks to those prompts, they can have a big impact on what the model spits out. Now, another thing they looked at was how to pick the best team of aspect verifiers for each task. Did they just throw all their verifiers at every problem and hope for the best?
That doesn't sound very efficient, does it?
Not really. They actually had a more strategic approach. They called it Verifier Engineering. It's kind of like prompt engineering, but instead of focusing on the instructions, you're focusing on picking the right team for the job.
Okay, so how did they go about engineering these domain-specific teams of verifiers? Did they have a system?
They started with their pool of 20 different aspect verifiers. Then, for each domain, they picked a subset that consistently gave the best average performance across all those generator LLMs. They tested it on a validation set first.
So they were letting the data guide them. They basically ran a bunch of trials to see which combo of verifiers worked best for each type of problem.
Exactly. It's like a coach putting together the best lineup for a game. But for AI verification, they were tailoring those teams to the specific challenges of each domain.
Got it. But what happened if they skipped all that verifier engineering? Like, what if they just used all 20 verifiers for every problem? Did everything fall apart?
Not at all. Even without any fancy tuning, the results were still pretty decent. Using all 20 verifiers, it was generally competitive with self-consistency and that reward model verification.
So even a brute force approach, it can still get you somewhere. But it sounds like that targeted verifier engineering, that's what really helped them get those extra performance gains.
Yep. It's the difference between having a good team and a great team. Having the right mix of expertise, that synergy between the verifiers, that's what can really take those results to the next level.
Okay, so we've talked about how they design those prompts, how they pick their verifier teams, but now I'm curious, what happens when those verifiers actually get to work? Can we see some examples of them in action?
Absolutely. The paper actually walks through a few examples to show how different aspect verifiers, each with their own focus and strategy, they can team up to find errors or inconsistencies that one verifier might miss on its own.
Oh, I'd love to see one of those examples. Can you walk us through it?
Sure, let's take a look at the one they give for the math data set. They've got this problem where the generator LLM, it came up with a wrong answer. And in this case, the first aspect verifier, it was using the simple direct approval strategy, and it actually approved the wrong solution. It missed the mistake.
So even a simple verification method, it can slip up sometimes. It's not foolproof.
Right. But that's where the power of the team comes in. They then show a bunch of other aspect verifiers, each with their own approach, carefully looking at that solution.
So you might have one verifier checking the math in each step, another one looking for logical errors, and maybe another one trying to rephrase the solution to see if it makes sense.
Exactly. It's like a team of detectives, each with their own style, combing through the evidence. And in this example, they show how those other verifiers, by working together and looking at the problem from different angles, they're able to pinpoint that error in the solution.
So even though the first verifier missed it, the team as a whole, they were able to catch the mistake. It's like that collective intelligence at work.
That's the beauty of diversity and collaboration, even when we're talking about AI. Now, to really drive home the point, they actually go deeper and show how these different base LLMs, even when they're using the same verification strategy, they can come up with totally different evaluations of the same aspect.
Wait, so you could have two verifiers, both tasked with checking the logic of a solution step by step, but they might reach different conclusions.
That's right. It's like having two judges at the Olympics using the same scoring system, but giving out completely different scores for the same performance.
That's a little unnerving, isn't it? It's like even when you try to make things objective with these well-defined verification tasks, there's still this element of subjectivity based on which base LLM you're using.
It really highlights that choosing the right verifier for the job, understanding those strengths and weaknesses of each base LLM, it's super important. It's not just about having a bunch of verifiers, it's about having the right ones.
It's like putting together a team of experts. You don't just look at their credentials, you think about how their styles and approaches will mesh together.
Exactly. And that just adds another layer of complexity to this whole multi-agent verification world, but it also opens up some really exciting research avenues. What if we could develop ways to calibrate those judgments from different base LLMs so they're more aligned?
Or imagine being able to automatically pick the best base LLM for each task, based on the specifics of the problem and the characteristics of each LLM. That would be amazing.
There's so much potential here, it's really just the beginning. And these real-world examples, they really bring it all home. It's not just theoretical, this multi-agent approach, it actually works, and it works well.
Agreed. It's not just about finding errors either. This whole framework, it has the potential to boost creativity and innovation in AI by encouraging those systems to explore a wider range of solutions and approaches.
Imagine teams of AI agents working together, brainstorming new ideas, questioning assumptions, pushing the limits of what's possible.
That's a powerful image, isn't it? AI is a tool to amplify human intelligence and creativity. It's not about replacing us, it's about working with us, helping us achieve more than we could on our own.
And I think this research is a big step in that direction. It's not just a new algorithm, it's a whole new way of thinking about LLM optimization and verification.
It reminds us that sometimes working together, combining our strengths and perspectives, that's how we achieve truly groundbreaking results.
It all comes back to that idea. The whole is greater than the sum of its parts. And with that, I think we've covered a lot of ground in this part of our deep dive. We've gone from the nitty-gritty details to those broader implications. And I think it's safe to say this multi-agent verification, it's pretty darn impressive stuff.
I totally agree. It's been a fascinating discussion, and I want to thank you for joining me on this journey. Now, for everyone listening, be sure to tune into our final part, where we'll step back and take a look at the bigger picture. What does this research mean for the future of AI? What role might these multi-agent systems play in shaping that future? That's what we'll be exploring in part 3. All right, welcome back, everyone. So we spent the last 2 parts really digging into the nuts and bolts of this multi-agent verification paper. But now I want to shift gears a bit and talk about the bigger picture. What are the implications of this research? Where could it lead us in the future of AI?
You know, it's not every day you come across a paper that feels like it's truly pushing the boundaries, opening up new horizons. And this one, I think it really does. It's like it's giving us a glimpse into this future where AI, it's not just about building bigger and bigger models, it's about building these systems, these ecosystems of smaller, more specialized agents that can work together, learn from each other, and achieve things that none of them could do alone.
So it's like a shift from that one superintelligence idea to a more collaborative, collective intelligence approach, right? The strength comes from the team, not just the individual star player.
Exactly. This whole idea of multi-agent systems, it's not just about verification. This paper is like a proof of concept, showing us that this approach, it can lead to real, tangible improvements. But imagine scaling that up. Think about swarms of AI agents, each one with its own unique skills and knowledge, working together to tackle problems that are way beyond what any single AI or even a human could handle.
Okay, now you're getting me excited. We're talking AI teams, designing buildings, composing music, running scientific experiments, maybe even writing novels.
The possibilities are pretty mind-blowing, aren't they? But of course, with any new technology, there are challenges. We got to figure out how to design these multi-agent systems so they're robust, reliable, so we can trust them, and we got to make sure they stay aligned with our human values and goals. That's a big one.
It really makes you think about what intelligence even is, right? If we can create these systems of AI agents that seem to exhibit some kind of emergent intelligence, this collective intelligence, what does that tell us about our own intelligence? After all, we're social creatures. We learn and solve problems together.
That's a deep question, and I don't think there's an easy answer. But what I find really exciting is that this research, it's not just some pie-in-the-sky idea, it's giving us practical tools, ways to build more powerful, more flexible, and more trustworthy AI systems right now. We don't have to solve every problem ourselves. We can create AI systems that can help us work alongside us, like partners.
That's a really cool vision. This future where humans and AI were collaborating seamlessly, each bringing our own strengths to the table. achieving things that neither of us could do on our own.
I think that's the key takeaway here. This paper, it's not just a technical breakthrough, it's a shift in our thinking. It's about moving beyond individual models, embracing this idea of collaboration, diversity of thought, collective intelligence in AI. And that's something we can start doing today.
It's a powerful reminder that sometimes working together, combining our strengths, that's how we achieve truly amazing things.
Well, I think that just about wraps up our deep dive into multi-agent verification. We've explored the technical side, the experimental results, and even touched on some of the bigger questions it raises. It's been a fascinating journey, and I want to thank you for being my guide.
The pleasure was all mine. And to everyone listening, thanks for joining us.
Me too.
Keep those brains buzzing, keep exploring, keep pushing those boundaries. The future of AI, it's out there, waiting to be discovered.